Distance or smooth solutions to obstacle problems. Short.
Okay. Nice short title. So thank you very much for coming along. So just to put people's minds at ease, I'll maybe talk about a third or half of the slides. The rest are for kind of reference if anybody wants a copy of the slides. And they do, I guess they're so well organized, they give you this little red sticker or card saying where you can email your presentation to afterwards, and I guess it goes on the Newton Institute website. So, but if you want to email me as well, that's perfectly fine. Okay, so let me first of all, talk about the class of problems that I'm going to discuss, and then spend a little bit of time talking about why I think they're interesting and why they arise in applications. Then I had a PhD student actually solve some of these problems numerically, one of my PhD students, so I'll talk about a little bit of his work and some of the pictures that arise. And then the rest of the talk is really trying to show that those pictures that my student generated suggest that solutions to certain obstacle problems that I will discuss, and their free boundaries, have certain regularity and smoothness properties. I won't discuss regularity of the free boundary, but the goal of the talk is to try to show where in certain difficult situations why solutions have certain smoothness properties. So that's the goal. All right, so first of all, we need to talk about the operators that are going to feed into our problem. So the motivation, as I'll explain shortly, really comes from a class of two-dimensional problems, but it can be phrased perfectly easily in any dimension, so let's do that. So I'm going to take an operator which has this form. So A is an elliptic matrix, doesn't need to be constant. B, vector field. C, a scalar function. So scalar parabolic equation. Scalar elliptic generator. The key feature that makes it interesting is naturally this coordinate here. For just ease of talking about geometry, I'm going to discuss problems which are defined in a domain which is contained in the upper half space. So it's the boundary of this upper half space where xd is equal to 0, where all of the problems I'm going to discuss acquire a degeneracy. Naturally you could think about an operator defined in some curved domain where it becomes degenerate in the sense that this matrix here becomes 0 as you approach the boundary. But for simplicity, all the essential features are captured by degeneracy at a flat boundary. So I'm just going to make that simplification. Okay, so in this situation, it's sort of an observation that probably goes back to, I would say, the late 50s or early 60s, but certainly late 50s due to Gaetano-Ficcara, that it's useful to split up the boundary into several portions, and this idea has certainly become more prevalent. I'm going to split it up into two pieces. One where the coordinate is positive, and one where the last coordinate is 0. So I'm going to loosely refer to those as being the degenerate and non-degenerate boundaries. The coefficient functions, for our purposes, we can take them to be smooth everywhere, and they have bounds that you would expect or anticipate will be present from classical PDE theory, uniformly elliptic PDEs as you would find in Gilbart and Trudinger or Krylov or references like that. And the matrix A itself, it could be degenerate, but I'm going to assume that it's elliptic. So the degeneracy in the title of my talk and in the PDE is it's solely captured by this factor xd.
What is the surrounded S in C alpha S?
Yes. So you can think about S as being standing for special. So these are a modified class of Helder spaces, which I'm going to explain to you shortly. I'm going to give you their definition. So for now, their definition is modeled on that of the standard Helder space, but there's an important difference. So I'll tell you what that difference is a little bit further on. Yeah. So, yes.
The union of these two parts of the free boundary, does it give the whole free boundary?
Oh, there are no free boundaries here at all yet. It's just a fixed domain, and these are the fixed boundaries. So I won't, in this talk, I will not discuss regularity of free boundaries at all. So sorry if that was a hope. So this is kind of before we would get to, the whole theme of the talk is what we need to do before we get to talk about regularity of free boundaries. Although there are interesting questions which arise there, and I'll certainly at least tell you about those when I get to some useful, important pictures. Okay, so this is the setup. The dth coordinate of this vector field B, it's important that it at least have a sign. So it should be at least non-negative. It does make things easier if it's positive. Okay, so that's the setup. C, as always, for elliptic problems, that we assume it's non-negative at least. And occasionally, we assume it's positive or bounded below. Parabolic problems, I'm going to describe in this way. Coefficients can now depend on t. And what is this Helder space here? Well, I'm going to give you a precise definition a little bit later. But for now, let me just say that it's defined by mimicking the usual definition of the Helder space C alpha, except that we replace the Euclidean distance by this well, I'll call a cycloidal distance. I didn't call it a cycloidal distance function. It was called so by these authors, Daskalopoulos and Hamilton. And there's a reason for that. Geodesics under this metric happen to be cycloids. Okay, so why are such modified Helder spaces important? Well, we have a PDE with degeneracy. These pair of Helder spaces, you can think about this one as being where the source function is going to live when we solve an elliptic or parabolic problem. This one is going to be where the solution is going to live when we initially solve it using a Schauder approach. The reason that they're important is because we have a degenerate PDE, this space here where we look for solutions, it has a way of very nicely taking into account the degeneracy of the operator A. It's no accident that this negative power, or the coordinate, it's the inverse of the power that appears in the definition of the operator. So that's not an accident. So their role is something that I'll explain a little bit later. It's going to be an important theme in the whole talk that we won't prescribe any boundary conditions along where xg is equal to 0, except as that our solution have a certain minimal regularity property there. So the boundary condition where the PDE is degenerate is purely one that we say the solution is going to be smooth up to that boundary face. I'll say exactly how smooth a little bit later. And this kind of Helder space, it has a nice way of encoding that smoothness automatically. Okay. In fact, it's a property of a function in this space. Little calculation tells you that this is necessarily true if a function belongs to this space. So when you have this PDE being obeyed on this domain, then there is this boundary condition being the PDE enforces that boundary condition on this space for a function with this kind of regularity. Of course, it certainly will hold if the function has more regularity, but this is something like the minimal regularity for which this falls. Okay, so just a picture to kind of relate all of these different boundary portions and domain and so on. So what I call del 1, again, this is the black portion of the boundary is where we're going to explicitly prescribe a boundary condition, be it Dirichlet or Neumann or whatever. I'll always, for simplicity, talk about Dirichlet conditions. This portion of the boundary, which is unshaded, is where no boundary condition is prescribed. It's purely a regularity condition that we just ask the solutions coming up to here are have a certain regularity property. And it's, the magic, if you will, I guess it's not magic, but it's the property of maximum principles attached to this kind of problem, that such problems are well posed when no boundary condition along here except regularity, but Dirichlet or Neumann along here. So let me spend a little bit of time seeing why these problems are interesting and where they arise in applications. So I'll give you one class of applications in mathematical finance because they're very prevalent there, but I'm sure that they arise in other areas as well. Most likely in study of porous media, for example. So there are 4 classes of problems which financial engineers like to study, and they are. The first one is not a financially motivated problem, it's just a mathematically motivated problem. In other words, we want to understand this basic elliptic Dirichlet type problem, so we can understand 3 others which are direct mathematical translations of option pricing problems in the financial engineering industry. So this one I've already essentially described. For this one, the parabolic version of this problem, solving this parabolic problem corresponds to computing the price of a so-called European-style barrier option. The boundary condition corresponds to the barrier. In industry, this will usually be a homogeneous Dirichlet condition. And we prescribe data at the maturity date t of the option, the so-called payoff condition. And the barrier condition is normally prescribed here. So typically, it'll be 0 along here. It'll be something compatible there. And then the so-called perpetual American-style barrier option is the one kind of American-style barrier option, or American-style option pricing problem that you can solve explicitly, at least in one dimension. Will be to solve this problem here. And psi here corresponds in the financial industry to the so-called payoff function. You're prescribing Dirichlet data here along the piece of the boundary where the PDE is non-degenerate, and you're not saying anything about the boundary conditions where the PDE is degenerate. So to financial engineers, not prescribing a boundary condition where the PDE is degenerate makes a lot of sense because they have no idea what the solution to the problem should be there. So the rest of the data that you put in, boundary condition here, what PDE the problem should solve elsewhere, this boundary condition or this one, that should determine what the solution is where the PDE becomes degenerate, and there's no financial intuition for what the solution should be when the PDE is degenerate. So it's important that the theory kind of support that practical goal. Last one is the full regular finite horizon American style barrier option. So this is a parabolic obstacle problem. Describing data along the parabolic boundary, but cutting out again where the parabolic PDE is degenerate, and an obstacle function compatible with the Dirichlet data. Again, this needs to be compatible where the PDE is degenerate. You don't care whether or not it is elsewhere. So typically in finance, this would be the usual obstacle function for a 2-dimensional problem in this instance. Okay, so if we were to pursue this financial analogy a little bit further, this would be the kind of generator A that you see commonly arise in finance. So exactly this kind of structure, and this particular structure was proposed by an economist from the business school at Maryland, I think, where he still is, in about 1993 or so, as a replacement for the Black-Scholes model. Okay, and all the coefficients here have financial meanings, but if somebody wants to ask me about those afterwards, I'll explain what the meaning is. All right. So let me show you some pictures. As my PhD and I graduated, students spent lots of time generating these and many more. I just have a small selection from his thesis. So first of all, this is the solution to the PDE problem with no obstacle style constraints, just the elliptic problem. And we can draw a couple of conclusions from the picture. The solution looks indeed like it's perfectly smooth coming up to where y equals 0, which is nice. It also looks like it's perfectly well behaved along these corners. And the corners, as you might guess, in any PDE problem where the domain has corners, this one where a degenerate boundary meets a non-degenerate boundary, we're prescribing Dirichlet data or Neumann or whatever along here, no data along this edge. That may be a spot which is troublesome to treat analytically, and that turns out to be the case. However, as far as the picture suggests to us, it's well behaved there. And I should say this picture was generated, quite using carefully adapted numerical methods for the PDE in question, but finite element and finite difference. So we believe that the picture does represent, reality.
Here the coefficients are.
Pardon me?
Which are the coefficients here of A?
Oh, I don't know. I can tell you. I forget now. But if you're interested, I can tell you. In fact, I can just send you a thesis, and there'll be dozens of pictures plus what the coefficients are. Okay, so this is the picture where we have an obstacle. This is the obstacle down here graphed, and this is maybe it's possible to vary the parameters a little bit more. I probably should have, so that you get more of a substantial meeting of the solution with the obstacle. But here you can see that it is meeting the obstacle along a small free boundary portion there. Again, as far as we can tell, the free boundary looks like it's smooth and quite well behaved, and it's also looks like it's it's meeting where the PDE becomes degenerate here and here, and doing so in a quite well behaved way. Now, showing that the solution, the free boundary does have this nice behavior here is of course another matter. So both of those problems, describing the behavior of the free boundary here or here or is tricky. Okay, so let me talk a little bit more about this family of Helder norms. So these were invented in Herbert Koch, actually independently by two groups of people. One by Herbert Koch at the University of Bonn, I think it was at the time, in his Habilitations thesis. He recognized that by changing the usual definition of Helder space to use this function rather than Euclidean distance, that gave you some advantages in developing a priori estimates for solutions. Independently, Richard Hamilton and Todi Daskalopoulos had the same idea, basically the same year. So the definition, at least of the C alpha spaces, goes just as the usual definition is. You just replace Euclidean distance by this one.
This is a kind of hyperbolic distance, right?
Well, not quite, because it's it's xg, not xg squared. It's okay. So that we could just integrate this metric and find distances defined by this metric, but it's that gives you a messy formula. It's convenient to just use one which is equivalent to the distance function defined by this metric. So this is there, and there are different choices. This is one choice which is easy to use. Koch uses one choice. Daskalopoulos and Hamilton use a different choice. Because whether or not the domains, pieces of the boundary are attached to the domains are not, is important in definition of various function spaces and also in describing regularity of the solutions, which domain boundaries they're assumed to be smoothed up to and which ones they're not. It's convenient to just introduce a little bit extra notation to describe that. So O at the lower bar, O at the upper bar is the usual one, I'll just throw in the boundary. O at the lower bar just means that I throw in the piece of the boundary where the PDE is degenerate. And it's a general rule of thumb in doing any calculations that you should treat this piece of the boundary as really the interior of the domain. So this is particularly true of maximum principles, for example. If you take a classical maximum principle, then any statement that applies to the domain interior, this will you can just consider points as also lying on this piece of the domain boundary, even though it's on the topological boundary. And I'll give you some examples just to explain what I mean by that a little later. So the usual C alpha norm defines in the usual scheme, except that this distance is not the usual one. It's the cycloidal distance function. And then once you have that, then all the other types of variants of Helder spaces follow in the way you might expect, but there's one catch, which is also important. So I want to explain what that is. So one might think that, to get a CK alpha S space, we just do the obvious thing. But that turns out to not be a good idea. For C1, it's fine. This is just the usual definition, just distance functions. Standard distance function replaced by cycloidal distance function. However, for the C2 space, which is the range, the domain of our PD, we're going to modify that pattern. And in the case of second derivatives, we're not going to take the C alpha S norm of the Hessian matrix, but rather we're going to multiply that by the coordinate xd. And again, the motivation for that is that the appearance of the xd here is, again, it's not an accident. This combination of second order derivatives, we should think of it as being roughly comparable to the combination of second order derivatives we see in our PD, where this factor also appears. So the appearance of this factor here is, again, is reasonable. So it's these choices make standard looking a priori estimates from the usual sources translate into a priori estimates for this degenerate PD. That said, they are much harder to establish than they are in the non-degenerate case. But that's another story. Okay. You'll occasionally see me use notation like this. So this, this just simply means that the function u has this regularity property up to the portion of the boundary where the PD is degenerate. This means it has it everywhere, up to every boundary portion. And again, one property of these Helder spaces, which I noted earlier, I'll emphasize again, it's not sort of explicitly baked into the definition, but it's a simple consequence that functions in this space obey this property. So, in particular, if you have a function u in this space, it doesn't mean that it's C2 up to the boundary or C2 alpha up to the boundary. It means that, xd times that function has a certain kind of Helder regularity up to the boundary. So, it's not immediately obvious that this would hold. Of course, you could ask, well, why not just ask for that regularity right up front? But then, doing establishing an a priori estimates and showing, from the start that a solution with more regularity than is initially apparent might exist is hard. So you want to start with the minimum regularity that seems reasonable for the problem at hand, and then show it actually does have more. All right. So with that, let me state the main results, and then try to sketch the main ideas behind them. So I'm going to spend just the interest of time and just talking about the main difficulties in a smaller number of cases rather than lots of little things in a larger number of cases. I'm going to restrict my attention to the elliptic problem, the boundary value problem, and the obstacle problem, and things for the parabolic version of those problems. They carry over in a similar way. So, so we have a partial Dirichlet problem, Dirichlet data being just specified on the portion of the boundary where the PD is non-degenerate. And I'll assume these conditions. The A matrix has a uniform ellipticity property. This BD coefficient is positive, and the C is non-negative. And then occasionally I'll throw in other conditions as well that, certain coefficients have slightly stronger boundedness properties or positivity properties. Yes?
Do you use magnitude for what's happening?
Pardon me?
If BD is negative?
If BD is negative, that's an interesting and separate problem. Yeah.
So
Yeah.
this actually appears in study of shock reflection, and then we can prescribe conditioned.
Yeah. Thank you. Okay, so I'm trying to be probably a little bit overly complete in mentioning all of these conditions, but again, occasionally people ask me for copies of slides after I give a talk, so thought I'd be more precise than less. And this is, again, a shorter version of what's in the actual paper, which you can find on the archive. So, so the upshot is, provided the coefficients of the generator A has conditions, obeys conditions in the spirit of those that I've explained. If you look for if you're given a source function, which is in this nice Hilbert space and bounded and the bounded Dirichlet data, then there's a unique solution in this space. And we should kind of pay attention to what we say about the regularity of the solution and what we don't. So what this is saying is that the solution has this special kind of C2 alpha property. It's C2 alpha in the usual sense, standard sense on the interior, and has this modified Koch or Daskalopoulos kind of regularity up to the flat boundary portion where the PDE is degenerate. So it might be C2 or better, C2 alpha up there, but it might not. And it's continuous on the, it's bounded, it's continuous up to the non-degenerate portion of the boundary. What's not said is it continuous up to the whole topological boundary. This problem is still, it's well posed. Maximum principles, suitably adapted will tell us that. But showing that the solution is even continuous around the corner points is tricky. Now, it is possible to do that. I won't talk about that today, using different methods, variational methods, but it seems to be tricky to show this using Schauder methods, let alone if the boundary is suitably smooth, that it has more regularity. So while the picture that I gave you a short while ago of a solution did indicate that the solution with reasonable data should be smooth up to the boundary everywhere, it appears to be hard to show that, even hard to show that it's continuous up to those corners. Again, I think anybody who's studied boundary value problems on non-smooth domains is familiar with that kind of problem. All right. For the obstacle problem, again, same partial Dirichlet boundary condition, we're just throwing in an obstacle now. So in this instance, it's again a little bit complicated to describe what the regularity is. It's expressed in several different pieces. So I'm going to call omega the non-coincidence set. We're given, in addition to everything else, we're given an obstacle function which is compatible with Dirichlet data where the PDE is non-degenerate, bounded above. And the obstacle function has this, this kind of regularity. So C2 up to where the domain is becomes degenerate, and continuous up to the non-degenerate boundary. And then the conclusion is a little bit more complicated than it was before. This continuity statement, no change. It has a regularity theory which we might infer from just our usual theory of obstacle problems on the domain interior, but also up to this boundary portion where the PDE is degenerate. In fact, in separate work with Daskalopoulos, we showed, as expected, it's C11 in the interior, no problem with that, but it's also C11 up to where the PDE becomes degenerate. So that was the extra content in that paper. And then has expected regularity for an obstacle problem in the interior, and then has this kind of regularity, not surprisingly, on the non-coincidence set. again, the surprising part perhaps is also, it includes, where the PDE becomes degenerate. Okay, so, several different moving parts to that. And these are mostly technical comments, so I think I will, in the interest of time, skip over those. Okay, so so let me talk a little bit about the maximum principle for these problems and why the problem is well posed to begin with. Any of you who have read Ficara's papers or any of his successors will know that there are different versions of the maximum principle for degenerate PDs. The ones I'll give you, I think, are a little bit different in flavor because they make no distinction about the so-called sign of the Ficara function that Ficara defined in his papers. Rather, we just ask that the solution have a certain regularity property up to where the PD boundary, where the PD becomes degenerate at the boundary. So, just to give you an example, there are no undergraduate students here, for better or worse, but let me recall nonetheless one of my favorite classical ODEs, the Kummer ODE. So fundamental solutions, the confluent hypergeometric functions. And then the two fundamental solutions, they have different properties, regularity properties, up to where x is equal to 0. So function m is smooth up to the boundary x equals 0, whereas the function u is continuous up to, but it is not smooth in any sense up to. And the coefficients a and b here, just as they will be in the financial problems, they're positive. So if we require that the solution be C2 in the interior, smooth up to this boundary portion and continuous on the whole thing, and have boundary data prescribed only on where that edge, x equals L, then that gives you uniqueness. So that little baby example, toy example, it tells you kind of what to expect from maximum principles in general. And in particular, tells you that even for strong or weak maximum principle, it doesn't matter. You should treat x equal to 0 as being part of the interior. So, so if we go back to the general case, the strong maximum principle, then it is just reads like the usual strong maximum principle, except we're allowing for u to attain a maximum, not just in the interior of O, in the topological interior, but also on a piece of the boundary where the PD becomes degenerate. It can still be constant if it attains a maximum on that piece of the boundary.
Again, how you tell apart the two fundamental solutions in the use you are going to do?
Well, I didn't write down expansions for them or anything like that, but I just, I'm just kind of quoting from Abramowitz and Stegun, for example, where you can find them explicitly, that the two fundamental solutions, they have these regularity properties. M is smooth up to this point, endpoint, x equals 0. The other function u, the Trichomy function, this is continuous up to x equals 0, but it's not C1 or better. So that's the distinction between the behaviors. They have different asymptotic behaviors as x goes to infinity as well, but that's, I'll ignore that since I'm looking at a finite interval. Yes?
Are your solution correspond to this first function?
Pardon me?
Your solutions, do they correspond to first of these fundamental solutions? Solutions that you're considering?
Exactly, they correspond to the M solution. Yes, precisely. Yeah. So it's that's precisely what we're doing. We're asking that our solution have a minimal degree of smoothness, let's say C1 or better. So this kind of solution U is being excluded, and the other solution is being admitted. Of course, we could prescribe a Dirichlet condition at x equals 0, 2, and then we'll have both. Yeah.
The case of I mentioned about the possibility prescribing with B negative, you have smoothness.
Yeah. No, I'm always in this regime where positive constants. Yeah.
It's different.
Yeah. Okay, so strong maximum principle, and then weak maximum principle. Again, it says what you expect. Provided you replace in the usual definition boundary by non-degenerate boundary portion, then everything reads as you expect. And in fact, just by mimicking the usual proofs of these things, you can get this. There are parabolic versions of both of these statements as well. The strong maximum principle for the parabolic case, as usual, is a little bit trickier to show. Okay, so I will skip over that. It's possible to prove ABP type results as well. I won't get into that. Okay, so in fact, let me not dwell too much on maximum principles. Otherwise, okay. So let me move. So that's more or less covers why we expect our solutions to be unique if they exist. Let me turn to the question of how do we show that they exist in the first place. So. So for this, as my example with the confluent hypergeometric function indicated, obviously if you have a one-dimensional problem, you can find explicit solutions, model solutions. If you have a multi-dimensional problem with constant coefficients, but this kind of behavior in the vertical direction, xd direction, then you can also find model solutions just by Fourier methods. Okay, so the one other feature of this problem, which I have kind of indicated several times, that there are corners where the non-degenerate portion of the boundary and the degenerate portion meet. That turns out in of itself to be a difficulty which is a little bit unusual. So, and Daskalopoulos and Hamilton have I think a fairly well-known paper on the porous medium equation, regularity of solutions and the free boundary and so on, back in 1998. Koch's habilitations thesis from 1999. They both considered two situations where there is only one kind of boundary, the degenerate boundary. There is no non-degenerate boundary. There's no issue of corners or where the two styles of boundaries meet. So in Koch's habilitations thesis, he essentially, a large part of it is coupled with restricting, and both of their paper and his thesis, they're considering a model problem on the upper half plane, where it is, the only boundary is just the boundary of the upper half plane. So no corners or issues of compatibility there. In the porous medium problem, they're thinking about a blob of fluid or whatever, and the entire boundary in that instance is where the PDE becomes degenerate. So. This degenerate boundary portion is the whole boundary, and their problem is well posed, needing only to prescribe regularity of the solution up to this now topological boundary, and nothing else, no sort of explicit exogenous boundary condition. So they don't run into this this issue here, and this I probably won't have time to mention exactly why it's such a problem, but it is a problem, and I think it was probably first identified by Cohn and Nirenberg in a paper from the mid 60s. There's a little section in there on compatibility issues which arise in degenerate PDE problems, and they essentially sidestepped this issue. So so the one thing that the kind of estimate that Daskalopoulos and Hamilton developed, it's formally looks very similar to this. So using the same style of Hölder norms. The difference is that for them, the topological boundary is also the boundary of the PDE, where it becomes degenerate. So they only need to consider a global estimate like this, where the entire boundary is degenerate. There are no corners. the other kind of shadow estimate they develop is for an interior one for the upper half plane, where there's no issue of compatibility there either. So this is the paper where at least hints of these kinds of difficulties first appeared. So if we could, however, for this R-degenerate PD problem where there are the two styles of boundary problems and there is a corner, if we could develop some kind of global shadow estimate, then standard methods would just give us a solution. There wouldn't be any problem. However, it's the fact that we can't so far get a global estimate like this means we have to try to develop some alternative scheme for for producing a solution. One approach, as I mentioned, could be using viscosity solutions and show that they're smooth enough. But then if you'd use a viscosity solution approach, you'd still have to wrestle with, you'd have to use a framework which treated these two different kinds of boundary portions and adapt the usual viscosity methods. So the scheme I'm going to describe uses a version of the Perron method for which essentially interior estimates are going to be good enough. So, so the first thing is if we can't get a global shadow estimate of this kind, we at least do have an interior shadow estimate. And this was developed with my former PhD student, now a postdoc at UPenn. For functions in the space. The one other, and this will be important, the one global estimate we could get is for a solution that's defined on the whole upper half space or on a what we call a slab, just a strip, an infinite strip. But it's important that the strip be infinite. And we'll see why shortly. So then once we have that, the one Dirichlet problem we can solve is for a function u in this C2 alpha S space on a slab, where again this is important that this is infinite, and then there are these. There's a typo here. This should be del 0. This is a degenerate boundary portion. So there are the two boundary portions present, but because the domain is infinite, the two boundary portions don't meet. So there's no kind of corner point issue. So this turns out to be the one case that one can solve. And the way one solves it is first of all you imagine that A has constant coefficients, and then you can use these Kaplan-1 hypergeometric functions to produce a solution by hand using Fourier methods, and then perturbation theory and so on gets you the case of continuous coefficients. Now the next step is knowing that you can solve the problem on a slab is to consider a map from the slab to a half ball. Because for Perron's method, normally non-degenerate boundary and solving the usual kind of Dirichlet problem, we'll just consider lots of little balls around points in my domain. For this particular kind of problem, where part of the boundary where the PD is degenerate is being treated like a piece of the interior, we need to also consider half balls. And of course, there's a nice map from the half ball to the infinite strip. So if I can solve my Dirichlet problem as we can on a strip with a nice estimate, I can also solve the Dirichlet problem on a half ball. I won't get as nice an estimate. If I take a half ball and I stretch out the corner points to make it into an infinite strip, of course, bad things are going to happen to coefficients, but we can still solve the problem. So with that, then we need to develop a modification of the usual notion of continuous subsolution and supersolution, which are appropriate for these kinds of missing boundary condition situations, and then define a solution by the usual Perron scheme, and then show that does attain the boundary condition that is standard, and that it solves the problem. Okay, and there's a similar scheme for the obstacle problem. So, so the the observation is boils down to just a simple one, that half disk in 2 dimensions conformally equivalent to an infinite strip. And that example is nice because you can actually track through exactly what happens, the coefficients of a model PDE, and get a very precise idea of what this map does to the coefficients. And then one just generalizes that. As I mentioned, our degenerate PDE problem is really, you can view it as a kind of a mixed, boundary value problem with Dirichlet data on the curved boundary where the PDE is non-degenerate, and then some kind of nonlinear oblique boundary condition where the PDE is degenerate. So we can really think about it as being a mixed boundary value problem. When we have certain kinds of nonlinear boundary value problems, we have work of Barl and Ishii, which give us viscosity solutions in those situations. But you can't actually take the results just as is and apply them to this kind of discontinuous kind of boundary condition. One has to do some work, so at least partially rewrite some of their paper. So I prefer not to do that. All right. So what's the geometry then of the situation? This is where we can solve a degenerate PDE problem. Degenerate along here, Dirichlet data along here, non-degenerate. We just map such solutions onto the half disk, and do the same thing, of course, in higher dimensions. So for the obstacle problem, sorry. For the obstacle problem, how does it differ? Broadly similar flavor. First of all, have to develop a suitable notion of subsolution and supersolution that's adapted to this missing boundary condition situation, and comparison principles for them, and then adapt the usual Perron method for showing a solution to an obstacle problem to this degenerate situation using these notions of continuous supersolutions. Okay, so let me just explain a few of the results, and by the way, this is joint with my former PhD student, Camelia Pop, an interior estimate for these things. So this is something that we thought would be a parabolic version of this kind of result, was something that was developed by Daskalopoulos and Hamilton, and we thought we know it's true in the parabolic case. We thought it would be very simple to just take the parabolic result and just translate it to an elliptic setting. But it turns out to not be the case. So I guess there isn't always this perfect symmetry between parabolic and elliptic. So it turned out that this genuinely required some new thinking and tricks. But here it is. We're assuming that the solution is at least C1 up to where the PDE is degenerate. This combination of derivatives is continuous up to where the PDE is degenerate. The source AU has this regularity, and we're imposing this boundary condition. And then the conclusion is a regularity type of one, that the solution is actually a little bit smoother. It has this regularity property, so it's strictly greater than implied by these conditions here. And then on each subdomain, the usual kind of expected thing holds. The only thing that's noteworthy here about the subdomain is that it's not the usual compact subdomain. It's this is so it's that kind of subdomain where the degenerate domains pieces of the boundaries overlap. So let's see. For the infinite slab it turns out that provided the coefficients are bounded enough, then you can get a global estimate. And again, this is the kind of the perfect situation, if you will, where degenerate, non-degenerate boundaries don't meet, so you have this nice uniform geometry, and then you do get this global estimate. We suspect that it should be possible, but it requires new ideas to get the corresponding estimate where you have the corners in the domain. So then, once you have that, you get existence of uniqueness of the Dirichlet problem on a slab, which is all this is saying. And then compatibility of corner points I will skip over. So the the one thing it's interesting to do, occasionally some of these calculations or estimates can get a little bit tricky, and it's not clear entirely, what one would expect or not expect. But if you take a model PDE, which is this one, the model two-dimensional PDE with the model degeneracy, then this is simple enough that using just usual complex analytic techniques, you can translate this from a slab to a half ball and back again. So it's this is the form of the PDE on the half ball and the usual coordinates. If we map this so the mapping I'm using is just the usual one, taking the half ball to the quadrant and then to the plane. Then if we do that map here to change coordinates in this model PDE, it turns out that in the new coordinates given by that conformal map, it looks like this. So the second order part, the degeneracy is preserved exactly the same structure. And then the only issues are, well, what do these coefficients, B1 tilde, B2 tilde, C tilde, and F tilde, what do they look like? And they, as you might expect, have certain growth properties as you go out to infinity. The S coordinate is going from minus infinity to plus infinity. Theta from 0 to pi over 2. So they have certain growth properties in both directions, and so that the C tilde and F tilde. But as you approach the degenerate boundary, all those coefficients and functions, they behave nicely. All right. So then I know there is another talk in about 5 minutes. So I know Andrew is talking then. So, pardon? 20 minutes. Oh, it's 3. Oh, okay. Okay. All right. I'm sorry. All right. Okay. So let me just in the last few minutes, let me just the key thing with applying Perron's method is an appropriate choice of what you mean by subsolution and supersolution. So the only thing I might mention is just, well, how do you modify the usual definition? So we're going to call a function a continuous subsolution on a domain. When we restrict that to a ball, the usual thing happens. But if we restrict to a half ball, then we only take into account the non-degenerate boundary. So there's the maximum principle for these degenerate PDE problems plays a role there. All right. The one other thing, just because it has a cute picture, let me. So you modify the usual definition of subsolution, supersolution, and then with that, then the rest of Perron's method more or less continues. There is a corresponding notion of supersolution of the obstacle problem. Let me not go into that. Let me close just with a comment about the strong maximum principle. Just because there's a cute picture, so the strong maximum principle, of course, for both of the Perron any of these Perron methods is important. For the parabolic problem, it's a little bit trickier to prove, but there's a nice kind of proof using a little bit of geometry. So let me describe that. So we're looking at the coefficients have the usual nice properties, and we're given a subsolution. So my sign convection is that this is a subsolution, and u is a positive maximum. Then the usual things, u is a constant. So a key thing, if you remember from, let's say, Friedman's proof of this, or Nirenberg's, is a so-called Hopf-type lemma, which goes as follows. You're looking at an open subset of space-time, a subsolution, supposing it has a positive maximum, either in the topological interior or where this domain becomes degenerate. And you're also asking that you have not a ball rather, but an ellipsoid, I guess it could be a ball, touching the boundary. And then x star is the center of this ellipsoid, and you have this strict inequality on the ellipsoid, and then u achieves this point M at a boundary of the ellipsoid. So then the center of the ellipsoid and this tangent point, the spatial coordinates have to coincide. So one can, if one takes the usual proof with the strong maximum principle, the Hopf lemma, in this degenerate PDE situation, it turns out to be a little bit tricky, and it rests on our identifying a suitable barrier function. But in this instance, it's not quite so easy to identify a suitable barrier function. So we're going to ask for one which is positive on the ellipsoid interior, 0 on its boundary, negative outside the closure, and this happened to the test function on this ball. So p bar is appearing in is this point here. Sorry. And so Friedman's choice of barrier function is this, and this works fine in the non-degenerate case. But there's it's analogous to the Gilbart-Schrödinger, the standard choice. But the standard choices, they make use of the fact that either the elliptic operator A or the parabolic operator A, they're strictly elliptic, strictly parabolic. But when that's not the case near this point, it's not so clear, how to choose a barrier function. So the trick is to kind of just apply a coordinate transformation just to modify the geometry, so that a choice of barrier function becomes more obvious. So this is kind of a heuristic picture of the situation that we're given. Our interior ball or ellipsoid, touching the boundary. This is the degenerate boundary portion. This is what the 0 means. Q is our space-time and is some just large neighborhood. And again, the spherical geometry here would suggest a certain kind of barrier function, or elliptical geometry would suggest a certain kind of barrier function. So rather than use that, let's apply a coordinate transformation, which basically just pushes this picture downwards. So we get something like this, where the colors represent, where things have mapped to. And now this is, the boundary of the upper half plane, and it's a little bit clearer to guess what a suitable barrier function is in this instance, and it turns out that just the simplest one, imagine, works, and then the rest of the proof then is fairly easy. All right, so I think rather than talk about beyond these PDEs, let me just, thank you, and stop. Okay.
Questions or comments?
How would you modify your Hilbert space to have a kind of similar result? Instead of having xd, you have xd to a power.
It's not entirely obvious. So, part of the reason is that xd to the power 1 has a certain scaling property, and then the proof of the so I had a certain shatter estimate there. I mean, we make use of scaling properties all the time, and the proof of that. So it's it's not entirely clear how that how that would affect things. In the variational setting, it's it's a little bit easier. You can be much more flexible about the power. So in a variational approach, which I didn't talk about today, you can have a power of xd, I think, up to the not 2, but anything less than 2, and that seems to work.
But you have
So.
Hilbert spaces there.
No, those are weighted Sobolev spaces. So there's probably a weighted Hilbert space approach too. I'm sure there is, but it seems trickier to identify what the what the right proof is.
In the use by Herbert Koch of this transformation, he used it to prove also high regularity. Can you do it in this case?
Yes. Yeah, you can show that solutions don't just have this C2 alpha S property up to the boundary; they're actually C infinity up to the boundary. Yeah. So yeah, one can show that. Yeah.
And how do you define the higher norms? Because in the definition of the C2 norm,
Yeah.
you introduce a weight in the second stage. No?
That's right.
You
Yeah.
keep on introducing weights every 2 norms.
There's the pattern. So for the odd k, it's the same as what I had for C1. You just take C alpha of all the kth order derivatives. For the in the case of the even, it's the same up to the highest order derivatives, and then for the even derivatives, you put in this factor of xd. It's that the higher order norms are defined in our papers.
Anything else?
Yes, on the other direction, what is the minimal regularity that you need for the obstacle in order to solve the obstacle problem? You need semi-regularity on the obstacle, or can you?
I assumed that it was C2 up to the portion of the boundary where the PDE was degenerate, and continuous up to the rest of the boundary.
For instance, just continuous obstacle.
You can up to the fixed boundary where the PDE is non-degenerate, but it's not clear how to handle an obstacle which is just continuous up to where the PDE is degenerate. It may be possible, but that was not clear. So I did use the fact that there was at least C2 up to the piece of the boundary where the PDE was degenerate. Yeah. So that's an open question. Yeah.
Can you give us an idea what happens at the corner points?
I wish, I can give you this pictorial idea what happens at the. So just to recap, and either the So let's go with the obstacle case. I mean, this is pictorially from numerical analysis. That's what tells that the solution should be perfectly smooth up to the corner points, but it. Okay, I agree. There's a little bit of a blip there, so let's skip. That's probably just some numerical thing. It appears like it's smooth up to the corner points, but showing that is I mean, there is a compatibility condition that appears to be important. They're just analogous to the kind of compatibility condition that you have if you're solving a parabolic PDE on a cylinder. It's between initial data and spatial data at where those two domains meet, two boundaries meet rather. So there was another question.
So you say there is C infinity in the sense of this norms regularity up to degenerate.
C infinity in the usual sense, yes.
What does it say about usual derivative? So suppose you have the C infinity in the sense of this degenerate norm.
It's C infinity in the Custer-based sense.
C.
It's just straight C infinity. Yeah.
Have you tried or seen what happens if the fixed boundary touches tangentially because I think that probably the reason why you don't see any singularity is because it's not tangential.
Yeah, I haven't, I haven't tried that. Yeah, no. I thought that looking at these infinite strips and then imagining that I kind of, close the ends of the infinite strip might give me some insight as to what's happening. But yeah.
If you were to look at the distance that you have as a Riemannian metric, then look at the Laplace Beltrami, would you pick up this coefficient xd?
Yeah, that's a nice question. In fact, there's a little couple of paragraphs about exactly that in the Daskalopoulos-Hamilton paper. So if you write the Laplace-Beltrami operator in this cycloidal Riemannian metric, it just looks like the usual the xd factor disappears and it gets just absorbed by the metric. So you get what looks like the usual Laplace equation.
But somehow it seems that you can think of a geometry where the flat part of the boundary just disappears in a singularity, and that at a singularity you would then impose a boundary condition. So that might be a reason that no boundary condition is necessary.
Yeah. That's true. Yeah.
First time to speak again.